Okay, so today, excuse me, I'm going to start section 2. And basically, this is going to cover how we came to the method that we use to describe where we can find electrons. So where we left off was with Bohr's model of the hydrogen atom. And when they electrified hydrogen gas, and it glowed with that pink color, just as a kind of a quick review, since you had a week off. The hydrogen glowed with a pink color, and then they passed that colored gas through basically a prism, and they got what's called a line emission spectrum. So there were very specific frequencies of light that was emitted when hydrogen became excited. So that's where we left off. The question now is, why did hydrogen's electron here exist around the nucleus only in certain allowed orbits with definite energies? Because we talked about you have the nucleus and you've got these orbits around the nucleus, and let's just pretend like those are evenly spaced, and that electrons can jump to different levels. And when they come back down to lower levels, they emit photons with a specific frequency that is equal to the difference in energies between both levels, right? So if I've got, just making up numbers, okay? So let's say this is level 10, level 30, and level 50. So if an electron is excited and it goes from level 10 to level 50, that means that it absorbed 40 in energy. And if it drops from 50 down to 30, that means that it emits a photon that has an energy of 20, okay? So the question now is, why? Why do they exist only in these certain energy levels? So why can't electrons exist in a limitless number of orbits with slightly different energies? Remember, it's like a stepladder. You are either in one energy level or another. There's no in between. So to explain why atomic energy states are quantized, scientists had to change the way they viewed the nature of the electron. So this goofy looking character is de Broglie, Louis de Broglie. And so we're now in the 20th century in 1924. He proposed an answer to this whole wave particle duality that revolutionized our understanding of matter. I'm going to warn you, it is quite mathy. I'm not going to focus just on the equations, but just as a general concept of how we came up, or how de Broglie came up with the explanation. So de Broglie pointed out that the behavior of the electrons in Bohr's orbits were similar to the known behavior of waves. So now we go back to the wave theory, but any wave in a limited space has only certain frequencies. And that makes sense if you think about it. If you think about, let's say you've got the ocean, right? So you've got your ocean. And if you take, let's say, a kilometer of space, you can have a range of frequencies that exist within that 1 kilometer. But if I have another area where it's just 1 centimeter, there's going to be a lot fewer frequencies that exist within that 1 centimeter than exist over the 1 kilometer. Does that make sense? Because you have a bigger area, so the frequencies can be much more than if you just have 1 centimeter of space, right? So he equated those two things together. So electrons should be considered as being in a limited space around the nucleus. So the electron waves can only exist at specific frequencies, just like the ocean. So according to E equals hv, the frequencies will correspond to specific energies, which are the quantized energies of Bohr's orbits. Okay, so the frequencies, which I think is this one. I can't remember, honestly. And it doesn't matter anyway. I'm pretty sure that's wavelength and that's frequency. So the frequencies match the energies in Bohr's orbits. Other parts of his hypothesis were confirmed by experiment because electrons, like light, can be bent or diffracted. If you don't remember what diffraction is, that is when you have a wave that passes through different media, like going from a solid to a liquid or a liquid to a gas, or even through a small opening, the waves are bent. And that's what happens when you take sunlight and you put it through a prism. The sunlight is going through the air and then it hits the prism, which is obviously a solid. It's not a gas like the air is. And so then the frequencies, the frequencies of the white light are split. And because each of the frequencies bends at a different angle, that's how you get the colors of the rainbow, because red bends at a different angle than orange and yellow and all the rest of the colors of the rainbow. So you basically split the colors that make up white light. Diffraction experiments show that the beams of electrons can interfere with each other, and interference happens when waves overlap. That's when I showed you, if you remember, the double slit experiment, which I think that's when this video comes up. When you have the electrons and you pass them through the two slits, you get the interference pattern on the back wall, which is basically having like a large spot in the middle, and then you've got these lesser and lesser spots on the side. That's an interference pattern. Oh, there we go. Okay, so now everyone's here. So the overlapping reduces energy in some areas and increases in other areas. So if you have two waves, basically, because waves obviously you have like that. And if you have two waves together, I'll just do, see, if you got a wave like this and they match, then the peaks are going to increase the energy and the valleys are going to decrease. But if you have a wave like this, and when you get interference, that's like this, then these two are going to cancel each other out, because you've got, or not, sorry, not those two. This peak is going to cancel, or sorry, this peak in red is going to be canceled by the valley of the blue here. And so that's what you get when what they call interference pattern. And I showed you that video already. Okay, so that was de Broglie. So we know that electrons are particles because we can measure the frequency of the photons that are ejected from atoms when they're excited, just like in the photoelectric effect, and just like in Bohr's experiments where he excited the hydrogen gas, and you get the very specific line emission spectrum. And de Broglie also then verified that electrons can also behave as waves, as shown from the double slit experiment like I showed before. So if electrons are both particles and waves, where are they? To answer this question, it's important to consider a proposal first made in 1927, so we're just 3 years after de Broglie, and this is by a German physicist named Werner Heisenberg. Heisenberg's idea involved the detection of electrons by their interaction with the photons. Photons have about the same energy as electrons, but trying to locate a specific electron with a photon knocks the electron off course because they have about the same energy. So there's always uncertainty when you try to find an electron, because in order to find an electron, photons are involved. So Heisenberg's uncertainty principle states that it is impossible to determine simultaneously at the same time both the position and the velocity of an electron or any other particle. So you can know the velocity of an electron, or you can know the position of an electron, but you cannot know both of them. Okay, so basically, to simplify all of that, because we understand that electrons are both particles and waves, and that a particle and a wave are measured differently. That's basically the bottom line of why you can't know both the position and the velocity at the same time, because if you know the position, you're looking at it as a particle. If you know the velocity, you're looking at it as a wave. And because electrons are both, you can't know both at the same time. That's kind of the gist of what they're saying. So a little meme I found, which is never ask a woman her age, a man his salary, or Werner Heisenberg, the simultaneous position and velocity of a particle. Ha ha ha. Thought that was funny. Okay, so we've got de Broglie, who said, yes, electrons are definitely waves and particles. Then we have Heisenberg saying, okay, if electrons are waves and particles, that means that we can't know both the position and the velocity of electrons. Then we get to Schrodinger, and this is what I mean when I say it gets mathy. I have no idea what that is at all. I just know that that's his wave equation, but what the variables are, I don't know. It's like, that looks like Greek. It probably is. But Schrodinger used the hypothesis that electrons have a dual nature to develop an equation that treated electrons and atoms as waves. So only waves of specific energies, therefore frequencies, provided solutions to this equation. With Heisenberg uncertainty, this wave equation laid the foundation for modern quantum theory. And this is how we mathematically describe the wave properties of electrons and other small particles. Basically, what that means is that we're going to use math to describe the properties of electrons in an atom. Now, electrons don't travel around the nucleus in neat orbits. And a lot of times when you see a diagram of an atom, you'll have the nucleus, and then you see like these nice little kind of planetary orbits around it. That's not actually what electrons do. That's not what an atom looks like. Instead, it looks more like this, where you've got regions around the nucleus called orbitals. An orbital is a 3D region around the nucleus that indicates the probable location of an electron. And this is when you talk about the uncertainty principle, a lot of it's based on trying to define about where you could probably find electrons. Okay, so according to Bohr's model, the electrons that are increasing in energy are going to be in orbits or orbitals farther and farther away from the nucleus. That's the general rule. The further away from the nucleus you get, the higher the energy you are. And according to the Schrodinger equation, the electrons in orbitals have quantized energy. But energy level is not the only characteristic of an orbital that is shown by solving the Schrodinger equation. So what we use to describe the orbitals, again, the orbitals are these areas where we're likely to find electrons. We use what are called quantum numbers. These specify the properties of atomic orbitals and the properties of the electrons in the orbitals. And this is what I want to focus on today. And the first three numbers are direct results from solutions to Schrodinger's equation. Again, not understanding Schrodinger's equation at all, but I can appreciate the fact that he did it. And then based on that, we have the 3 of the 4 quantum numbers. So the first 3 numbers are going to indicate first, the energy level of the electron, 2, the shape of the orbital, and 3, the orientation of that orbital in space. The 4th quantum number is going to describe the electron in the orbital. So the first quantum number is called the principal quantum number. This indicates the main energy level occupied by the electron. Number 2 is the angular momentum quantum number. This indicates shape. The third is called the magnetic quantum number. This indicates the orientation of the orbital around the nucleus, meaning that different shapes, if you turn or twist them, that's going to indicate a new orbital, because you can have, for example, one of the orbitals is shaped like this. So if I have a 3D, because of course this is all three-dimensional, so this is one of the orbitals, but you can also reorient that shape around the y-axis, and you can also reorient that shape around the z-axis as well. So that's the magnetic quantum number, is the orientation. And finally, the spin quantum number. This is the only quantum number that is not a direct result of Schrodinger's equation. This just indicates one of the two fundamental spin states. So what that means is that each orbital can hold a maximum of 2 electrons, and each of those 2 electrons has to spin in an opposite direction. So the spin quantum number is going to be either plus 1/2 or minus 1/2, and that's going to be basically spinning whether it's clockwise or counterclockwise. That's probably like the least important. Well, it's actually, it is important, but we don't really pay much attention to it anyway. So you'll get it when I explain it. Okay. So I'm going to go through and explain each of the 4 quantum numbers and how it explains where electrons are. So the principal quantum number is, again, the main energy level. You can see from the diagram, the main energy level of an atom. And this is symbolized by a lowercase n. The values that are allowed for the principal quantum number are positive integers only. This is where we get a bit mathy, but it should be hopefully not too difficult to follow. So positive integers only. And again, as n increases, because we're increasing in energy, we are going further away from the nucleus. And actually, what I want to do to try to make it, trying to do this, you'll do it later. Yeah, let me go through the 4 numbers first, and then I'll, because it, the part that I'm teaching today is like the hard part. But then when I relate it to the organization of the periodic table, hopefully it makes it more clear. So let me just explain the hard part first, and then I'll show you how it relates to the periodic table. Okay, so that's principal quantum number, positive integers only. The next quantum number, angular momentum quantum number, except at the first main energy level. So that means first main energy level, that's equal to n equals 1, right? Positive integers only. So for n equals 1, there's only one shape, but for anything above 1, they have different shapes. So for a given value of n, there are different shapes, and these are called sublevels. Angular momentum quantum number is symbolized by a lowercase l. I know it looks like an I, but it's a lowercase l. This indicates shape. Now, the values that are allowed are 0 and all positive integers less than or equal to n minus 1. Okay, so for n equals 2, actually, let me start with n equals 1. That makes sense. Okay, so 0 and all positive integers less than or equal to n minus 1. So for n equals 1, I think I start this on the next slide, but I'll just start it now. For n equals 1, what are the values for L? I should say L equals what? So we have 0 and all positive integers less than or equal to n minus 1. Well, for n equals 1, n minus 1 is still 0. So the only value for n equals 1 is 0. That's it. That's why, except at the first energy level, you have different shapes. All right, so let's go through it for each of the levels. So again, n equals 1. L is 0 all the way up to n minus 1, whatever that is. So if n equals 1, then this is 0. So L can only be 0. And for L equals 0, the corresponding letter designation that we give for the shape is S. Okay? Hopefully. The shape of S is a sphere. And it looks like that. That is the s orbital. Is everyone okay so far, or are you hopelessly lost? Okay, I'm assuming everybody's good. All right. What about for n equals 2? Oops. For n equals 2, again, L can be 0 all the way up to n minus 1. So for n equals 2, L is equal to 0, and n minus 1, that would be 2 minus 1, is 1. So you have two values, 0 and 1. We've already specified that for L equals 0, the shape is S, and for L equals 1, the shape is P. These are just the letters that we call the shapes. And the shape of P is the hourglass, figure 8, whatever shape you want to call it. Okay? Now we get to n equals 3. So we have, it can be 0, it can be 1, and L can be 2. The designation for L equals 2 is the letter D. So for energy level 3, we have 3 orbitals, S, P, and D. And the shape of D is that. Basically looks like 2 p orbitals together. And finally, for n equals 4, you have L can be 0, which is S, 1, which is P, 2, which is D, and 3, which is F. So all of these orbitals exist for n equals 4. But the shape of the F orbital is too complicated to picture, but I do have some examples to show you. So this is what 4fy3 minus 3x2y orbital, and the quantum numbers that this corresponds to is for n equals 4, L equals 3, and the next quantum number, which I haven't talked about yet, which is m equals minus 3. Since I haven't talked about m yet, then I'll just go through and show you the different shapes, right? So again, n equals 4, L equals 3, those are the same. But the third quantum number, which is magnetic quantum number, that's the orientation in space, right? Just like I showed you, if you've got the p orbital like this, or like this, or like that. Sorry about my terrible art skills. Those are the orientations in space. And so that's what the m minus 2 refers to. Okay, and there's another example. The way that we name the orbitals is that we use the principal quantum number first, followed by the letter of the sublevel. So for example, the 1s sublevel is the s orbital that's in the first main energy level, while the 2p sublevel is in the p orbital, but the second main energy level. Again, these are just the numbers that we use to describe the areas where we find electrons. Now, the third quantum number is the magnetic quantum number, because orbitals can have the same shape but different orientations. So the magnetic quantum number, which is symbolized by a lowercase m, is going to indicate the orientation. Okay, so for the s orbital, there is only one orientation because it's a sphere. It doesn't matter which way you twist or turn the sphere, it's going to look the same. So there's only one s sublevel. So there's only, one, like there's not more than one sublevel for s. But when you get to p, you can orient that in 3 different ways. And so there are 3 sublevels for p. Now, how we come up with how many sublevels there are for each of the shapes, the values allowed for m are whole numbers from negative L to L. So if L equals 2, then the orientations for that shape, you have -2, -1, 0, 1, and 2. So that's 1, 2, 3, 4, 5 different sublevels, 5 different ways you can orient that orbital in space. And again, we have L equals 0, that's the S sublevel. And if M, sounds like a math class all of a sudden, if M, the values for M that are allowed are -L to L, and if L equals 0, there is no -0. So that's why there's only one version of S. But if you have L equals 1, that's the p orbital, right? So you can have -1, 0, and 1, -L to L. So that's what M equals. So that means that you have 3 different p orbitals. For L equals 2, which represents the shape D, you can have -2, -1, 0, 1, and 2. Just like that's this one right here. So for D, there's a total of 5 orbitals or sublevels orbitals. I use them the same. And finally for L equals 3, that is F. You have -3, -2, -1, 0, 1, 2, and 3. So that's 1, 2, 3, 4, 5, 6, 7. So there's 7 F orbitals. Okay, so again, just to review and make sure that we all understand, we've got 4 shapes of orbitals, and each shape can be oriented around the nucleus in a distinct or unique number of ways. And we get that again from the quantum numbers, which come from from Schrodinger's equation. So because S is spherical and centered around the nucleus, there's only one possible orientation. If you just use your common sense and you think a sphere, you can't orient the sphere in different ways around a central point. There's just only one way. Mathematically, when we use the quantum numbers, we say S is L equals 0, and M can be -L to L, but there is no -0. So there's only one S orbital. For P, again, like I've drawn, you can orient that around X, Y, or Z axis. So there are 3, but if we do it mathematically, again, P is matches the value of L equals 1. And for that, we get values of M of -1, 0, and 1 for a total of 3. So there's 3 P orbitals. There they are. So we can label them PX, PY, and PZ, PZ, whatever. For D, that's L equals 2. So M is equal to -2, -1, 0, 1, and 2. That's a total of 1, 2, 3, 4, 5. So there's 5 D orbitals. Okay, they're matching the values for magnetic quantum number. And there's the 5. Why, for some reason, this forms a ring, I don't know. And finally, oh, I guess I skipped F, but you do the same thing for F. Before I start that, so for F, that's L equals 3, which means M is equal to -3, -2, -1, 0, 1, 2, and 3. So there's 7 F orbitals. So S has 1, P has 3, D has 5, and F has 7. Okay, 1, 3, 5, and 7. Now, the final quantum number, and then I'm going to relate all of this to the periodic table and hopefully blow your mind because it's amazing how this matches up. So an electron in an orbital can be thought of, like I said, spinning on an axis. It spins in one of two possible directions or states. So the spin quantum number represents one of those two directions of spin, and we use the values +1/2 or -1/2. However, when we write electron configurations, which is a way of describing all of the electrons in an atom, we never ever actually go down to the level of spin quantum number. But it is important to understand that there's no two electrons that have the same 4 quantum numbers, and this is what accounts for that. Because the 4th quantum number, even if you have 2 electrons that are both in the 2nd energy level, they're both in the p shape, and they're both in the px orbital, one of them is going to spin +1/2 and one of them will spin -1/2. So no 2 electrons have the same 4 quantum numbers. Now, the most important thing, and this is what's going to relate to how I explain the periodic table in a second, a single orbital can hold a maximum of 2 electrons. Each of those electrons have opposite spins, okay? But the important thing to remember is that 2 electrons per orbital. Okay, I don't like that analogy, so I'm just going to skip them. All right, so here is how you break down the quantum number relationship to the electrons per energy level. So for quantum number main energy level 1, we have only the S sublevel. Remember, that's equal to all 0 plus all of the integers that are up to n-1, and that would be 0. So there's only S. There's only one orbital because you have negative L to L, and that's, you can't have -0. So there's only one S sublevel in level number 1. And then you can use these little shortcuts here. You've got the n squared and 2n squared, but you've got the number of orbitals per main energy level, or n squared, that's 1. There's 2 electrons per sublevel. Since there's only one sublevel, that is 2. So the number of electrons in energy level number 1 is 2. Now, when we break it down to level 2, we have both S and P. So again, everything for S stays the same. We have one orbital in this sublevel, and so that holds a maximum of 2 electrons. And we have the p orbital, which has 3 different, the p sublevel. And that's why I mean sublevel orbital, I get them mixed up all the time. I don't really care. But for p shape, that's why I like to call it a shape. For the p shape, there's 3 orbitals. Each of those orbitals can hold a maximum of 2 electrons. So that's a total of 6. And if you add up the s electrons and the p electrons, you get 8. For main energy level number 3, you add D, which has 5 orbitals, and that adds 10, so you get 18. And for n equals 4, you add the F sublevel, which has 7 orbitals, for an additional 14. So 14 plus 18 is 32. Okay. All right. All clear. All clear. Okay. So how do we apply all of that craziness to the periodic table? Because like I said, we're using these numbers to describe where electrons are. Now, the first thing I'm going to tell you is that the principal quantum number, or the main energy level, corresponds or matches the period number. Okay, so for period number 1, remember period is the one going straight across. For period number 1, that is equal to n equals 1. It's the same. So that means period 2 is n equals 2, period 3, n equals 3, period 4, n equals 4, like that. Okay, it's the same thing. So let's see what that means. All right, so you see this number here. This is energy level number 1. We only have the s orbital. Remember why? Because it's only L is only equal to 0. And so that's letter S. And for the number of orbitals per sublevel, that's negative L to L, but you can't have negative 0. So there's only one of them, and that can hold only 2 electrons. So if I go back to the periodic table, if you look at the, oh, let me go back here. Oh, hey. Okay, so period number is the same as principal quantum number. So for energy level 1, we only have one s orbital, and it can hold a maximum of 2 electrons. Now you look at how many elements are in period 1. We have 1, 2. That accounts for each of the 2 electrons that can be held by the 1s orbital. Okay. Now if we go to level, whatever. If we go to n equals 2, or the second period, we have for the second period, let me go back to this one. For second period, or the second energy level, we have both the S and the P sublevels. There's one S, but there's 3 P. The S can hold 2. Each of the 3 Ps can hold 2 for a total of 6. And so we've got 8 electrons in level 2. Let's go back to the periodic table. There we go. Okay, so how does this translate? We've got 1, 2 elements here. And how many elements do we have over here? 1, 2, 3, 4, 5, 6. There's not a coincidence that those match up. These 2 elements are the 2 electrons that belong to the s orbital in the second energy level. These 6 represent the 6 electrons that can be contained by the p orbital in the second energy level. If you come down here to the transition elements, how many elements are in the transition from group 3 to group 12? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons. Is there an orbital that holds 10 electrons? Yes, that is D. Right? D has 5 sublevels. Each of them can hold, or it's 5 orbitals, whatever. So like I said, I mix them up all the time. It has 5 orbitals. Each can hold 2 electrons for a total of 10. So S can hold 2, P is 6, D is 10, F is 14 because there are 7 different F orbitals. Now let's go to the periodic table and figure out which section represents F. Come down here. You actually forget these 2 because those 2 belong up here. So you start with CE. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Not a coincidence. This is all how you connect the organization of the periodic table with the 4 quantum numbers. And it's, wait, what time is it? It's 11:09. What time does this class finish? I think it finishes in a minute, right? 11:10. Oh my God. So yeah, sorry about blowing your head up until the very last minute. But last thing, what I want to show you is that groups 1 and 2, this is what's called the S block. Okay, so that represents the S orbital because each of those 2 groups that can hold a maximum of 2 electrons. Then you've got this whole block right here. That's what's called the P block because P can hold 6. And you've got 1, 2, 3, 4, 5, 6. And then you've got the transition metals. This is called the D block. This is where the d orbitals are. And then finally, you have the F block, which includes the 14 elements in the lanthanide and actinide series. That's the F block. So you've got S, P, D, and F organized on the periodic table. And with that, I'll see you tomorrow.